Okay, the recording has been started. Let me full screen this stream. Okay. So today I'm going to talk about Brownian motion and its relation to the heat equation. So let me start here. Brownian motion and the heat equation. Now, I'm not really going to talk about the physics behind the heat equation. That is well exposited in many other places. And I'm not a physicist, so I would assume that my value add is not there. But, let me get some water. So I'm more focused on the stochastic part of the, equation. And essentially, one views the Laplacian as like intimately related with this thing called Brownian motion. So what is Brownian motion? I'm going to describe it to you. So first, let's start off with some definitions. So a stochastic, by the way, I'm going to use the word random variable. I'm going to suppress a lot of measure theoretic technicalities because that's not useful to the exposition. But just know that there are a shitload behind the surface. So like, I can give many different versions of this lecture, and this one is going to look a lot different than the ones I would give in my like graduate level random walks and groups courses and stuff. Like, this is a much different lecture. So let's start with a definition. So the stochastic process, continuous. That is what we're going to work with here. Continuous stochastic process is simply a collection xt, where t is a real index of random variables, all defined on the same probability space. So oftentimes people restrict this indexing to 0 to infinity because they don't want to think about negative time. Same thing. So the way you should think about this is that we have this curve here. We have the xy plane. This is going to be time, t. This is going to be xt. And so given an event, omega, we're going to get path out some type of like random curve. This would be xt of omega. So this would be, in a sense, this collection is giving us a random curve for each event. And also, feel free to interject with questions. I'm not exactly looking at the chat because I'm recording. I guess I could be. Yeah. So feel free to interject with questions, just out loud because I'm not looking at the chat. Yeah, so in a sense, we're going to get a random curve for each like random event, for each event. And so one would ask, like, so what type of stochastic processes are there? What are the fundamental ones? What are their properties? And how do we study them? So let's start off with the easiest type of stochastic process. So examples. This would be the stochastic process, which is not stochastic. It's deterministic. This would be a drift process, so I could add a slope here, mu. And this is just deterministically giving me this line for any event. Now, this talk is about another type of stochastic process, which is also, so another type of stochastic process, which, okay, I'll give you another example, which xt are all identically distributed, so independent, identically distributed, and the probability that xt is, let's say, 1 is 1/2, and probability xt is 0 is also 1/2. So what does this look like? This is just like a bunch of independent 0-1 coin flips. So it's going to fill out like a dense part here and a dense part here. That's not very interesting because this is literally just like, just do like a continuum of many coin flips. It's kind of silly. So the real kicker here comes from when you start wanting to have like a dependent structure on these variables. You want like xt plus some epsilon to depend on, so let me see, want xt plus epsilon to depend upon, say, xt. But that's not quite right, because that's also a bad perspective. So I'll tell you why in a sec. So first of all, what type of things are we going to try to model here? So these processes were created to model things. What were they created to model? So initially, stochastic processes were created by a guy named Ito in near World War II. Stochastic processes were created to model diffusion. So if the heat equation is kind of a global perspective to diffusion, looking at like the distribution of like particles over time, the stochastic process point of view is a like minute or microscopic point of view of diffusion, where it looks at one particle at a time and sees what happens to that particle. And so this is where we come to the first definition of the day, and the most important one. Likely one of the most fundamental definitions in all of applied mathematics. A Brownian motion. Note how I wrote A. I will write the eventually, but I will not prove it is unique. Honestly, I will not be proving many things today. The reason is that this is a very technical subject and it's not exactly enlightening the proofs. A Brownian motion is a stochastic process. I'm just going to write SP for stochastic process, BT, which starts as time 0, so t in 0 to infinity. Again, I'm just going to start suppressing this like collection thing, such that satisfying these following 4 properties. So the first property is pretty silly. BT starts at 0, so deterministically our stochastic process is starting at 0. Okay, and it might be illustrative to put a diagram here that will update as I put more of the properties. So all we know now is that at time 0 we've got a deterministic 0. So that's cool.
Sorry, you mean B0 equals 0?
Yes, that's exactly what I mean. My bad. Yeah, BT equals 0 is just a line. Yeah, so B0 is 0 deterministically. Then now is where the interesting part gets on. So independent increments. So actually first, before we do increments, let's do, I forgot the name of this property, but basically what we want to happen is if you look at some t, bt minus s, we're going to want this to be distributed the same way as bt minus bs. And we're going to want bt minus s to be distributed like a normal distribution with variance t minus s. So what does that mean? It means that if I say I'm here, I start here, my Brownian motion, some curve, and now I'm started here. Let's say I go little jump epsilon, little jump epsilon. So this is BT, this is BT plus epsilon. I want this difference, so really I want all of these 3 things. Hold on. I want this BT minus BS distributed like this. So I want this difference here between BT plus epsilon and BT to be normally distributed, where the variance corresponds to how, like, the difference in time. So I should have a higher variance difference. Basically what I want is I want it to somehow be mean reverting. So I want at any point my difference between these two to be on average 0. But I want it to have a variance corresponding to how, like, far the time is. So I want it to, like, move sideways, but have bigger moves the further I go. So that's a natural condition. And the best way to think about this is try to model a stalk. Or a particle moving continuously to the side. So the third one is a bit less intuitive. This is independent increments. So we want, for a very discrete section of time, like this, I want these differences to be independent. I want bti minus bti minus 1, so t0 equals 0, to be mutually independent. So I want, essentially, if I cut up my space into here, and I have this curve going crazy, I want the differences on each of these sections to be independent. And last but not least, arguably the most important property, and also the most, like, kind of weird property, well, not weird, but, like, hard to ensure property, is I want, so with probabilities 1, so with probability 1, remember, a stochastic process is like a random curve. So I want, with probability 1, the curve that I get, with probability 1, or we say almost surely, so almost surely, the curve, which is just t maps to bt, is continuous. So almost surely I don't want something like this, where, like, almost surely this is not continuous. But this, I need it to almost surely be continuous. So I want some, like, crazy behavior like this. I want the further you get out to be, like, further variance and difference. But also, I don't want to jump. So these conditions are somewhat contradictory. I want to, like, jump further the further I'm out, but I don't want to actually jump. But I also want independence between the differences. It's like for some people these might be, like, clashing. So the question is, does Brownian motion actually exist? Does there exist a stochastic process satisfying these conditions?
But before we move on, I have two questions. One of them
Yeah.
is very stupid, but let me start with the stupid one. Random variables are defined as measurable maps from a probability space to some measure space. So the measure space here is the reals, but what is the probability space?
It's fixed. You can choose any probability space. It's fixed because the way that you work out this condition is you look at the push forward measure. So, like, if you view bt as a random variable from probability space omega to, say, the reals, then this condition is saying that the push forward measure bt star, so x has some probability measure mu, or p, I guess, for probability theory. This push forward measure is equal to, like, the push forward measure of the normal on, or is equal to, like, the normal function, the normal Gaussian density function.
Right, it does make sense to speak about in every probability space, but the point 4, it speaks of continuity, and for that we want to have some sort of topology on the probability space. Is that not the case?
It's continuity and measure.
Okay. I see. Okay, then my second question is point 3. Is it any different from requiring that any finite subfamily is mutually independent in light of point 2?
No,
it's the same thing.
Yeah, no, it's not. I mean, yes, it is different because this function, like, finite subfamily of differences, you mean? Because remember, these are the differences.
Well, no, but I mean, in light of point 2, the differences are the same thing as
yes, you're right. But then these differences have to be, like, different, Like, it matters where you cut.
But you can make forward and forward jumps. So say you have any family subfamily, AI, I mean BAI, say, that I can take.
Yes, you're right. Yeah, it is the same as any finite subfamily.
Okay, I see.
Yeah,
So any finite subfamily.
To me, it's just more intuitive to be that, like, yeah, so the finite subfamily being independent, that's more clarifies why it's harder to get these things to exist. But for me, this is a more, like, geometrically motivated condition.
I see, thank you. But it is the same.
Yes, it is the same. You're right. Those are good observations, yes. So yeah, now the question is, do they exist? Such that 1 to 4 hold. The answer is yes. But the way that you answer this is Kolmogorov extension theorem. Plus nonsense, which is, it's not exactly interesting. So there are a couple ways to there's plenty of ways to construct Brownian motion, but none of them are, like, actually interesting because of the fact that once you construct it, you can show that it's unique. So there exists only one. These 4 conditions uniquely specify a stochastic process. So there should be something fundamental about this process. It's a unique process that is not zero, and it's like, so there should be something fundamental, and that is what I'm going to try to depict to you now. So let's start with some properties. I'm going to get a definition here. If x and y are random variables, then their covariance is COV xy, and it's just the expectation of x minus its mean times y minus its mean. So if you think about this, if I did covariance xx, this is just the variance of x. So now when we have a Brownian motion, so okay, now we have the variance of x. So if we have a Rn valued random variable, so if x is Rn valued random variable, then it has a covariance matrix, which is given by, so x is going to be from some probability space omega to Rn. Then we have these coordinate functions, pi I. And so I'll call this composite here xi. This is now a random variable, a real valued random variable. And I'm going to say that the covariance matrix sigma x is the matrix of covariances, so between the coordinate functions xi and xj. ij. So let me do some adjustments to this definition to make things easier. So from this Brownian motion, you can construct Brownian motions with different variances. So note how this right here is t minus s, but I could have a parameter here which I'm able to set sigma squared. So it can really be whatever I want, so I can scale it by something. I can also choose a point to start by just discretely adding, so x starting at x of variance, different color, starting at x of variance sigma squared. Okay. So there are 2 parameters I get to choose, where it starts and what its variance is. And then that describes a Brownian motion for me. So some people will put an x here on the process to indicate that it's starting at x. I'll do that sometimes. So what is the covariance? So suppose we have now, let's do this here. Yeah, okay, let's do this here. Let's look at the process BT, which is just a bunch. So let B, how do I do this? Okay, I guess I'll just do BT1, BTN, B Brownian motions, independent Brownian motions. So then what I'm going to get is I can form a new Brownian motion BT, which is just coordinate-wise. BT1, BTN. And then I can look, so what does the covariance matrix of this look like? So BTS, or BT minus S, is going to look like, so covariance BT minus SI, BT minus SJ. So this is a computation for later that I'm doing. And since I've declared they're mutually independent, this is going to be a diagonal matrix. So identity n by n, scaled by t minus s sigma squared. So on the diagonal, we pick up the variances, and the off diagonals give us our independent structure. And since they're all mutually independent, these are just 0. Okay. So now let's get to the part where it was going to be a lot trickier because there are computations to do, and I don't have them written down. Well, I do, I just lost the notes. So let's do the heat equation. I claim that you can solve the heat equation with just Brownian motion. So, how do we do this? Let's look at an operator, a special operator called an infinitesimal generator of a process. So, what color shall I use? So I'll use this one. Definition. Given a stochastic process xt, the infinitesimal generator is defined by the operator, which, okay, I won't give you the domain of definition is where this limit makes sense. So it's a operator t, which is applied to functions. So spit in a point, and it will spit out the limit as, so a stochastic process starting at 0, spit out the limit as h goes to 0 of the expectation of f of xt plus x minus f of x. Wait, hold on. Yeah, there we go. Limit as t goes to 0. What am I thinking? Limit as t goes to 0 here over t. So this is kind of like a derivative. So basically what I say is look at what the value of f is. Take your point, run your stochastic process, look at what f is to start at x, look at what f, if xt started at, so actually it's probably better for me to do this with Brownian motion. So for bt, tf of x would look like limit t goes to 0 of take a Brownian motion starting at x, so btx, run it to time t, look where it goes, apply f, and then look where it goes, take off f at x, and then divide by t. So this is kind of like a derivative. But it's like a stochastic derivative. So let's compute this. I claim that you can actually compute this. Now, up to a sign, which I don't remember, claim, which will be somewhat surprising to people. My claim is that for an n-dimensional Brownian motion, t is Laplacian, plus minus. I don't remember which it is for n-dimensional BM. So this is what I mean by it's intimately related to the Laplacian, because essentially running, and what this means is this is like basically start at a point x and run Brownian. This operator is like running Brownian motion for an infinitesimal amount. That's why it's called an infinitesimal generator. So let's do this computation. So I'll look
Before we move on, somebody asked a question in voice chat who cannot speak. They're asking why a particle in 1D or 2D under Brownian motion returns to its original position.
That's a deep result. That's a very deep result that it's not super deep, but like it's not trivial to prove, and frankly it would take a long time for me to set up. So that's a question of what's called recurrence and transience. So the corresponding result is that given a neighborhood of, so I know more about the discrete setting here. For discrete random walks, this is like a continuous random walk. So if I give you a neighbor, let's say 2D, if I give you a neighborhood of the identity, the probability that after n steps, Brownian motion, 2n steps, Brownian motion, it's continuous. I swear to God. Okay, I don't know the correct result in the continuous setting. I only know the correct result in the discrete setting. But if we look at standard walk on like ZD, simple random walk, for D equals 1 to 2, this is going to be like discrete jumps in a lattice. And well, for D equals 1 to 2, this is going to be recurrent. And it's related to, okay, how do I want to say this? Yeah, I'm not going to talk about this right now. This is way out of the scope. I can talk about this later. Yeah, recurrence transience is like a deep result that I also don't have the tools to talk about this. I would need to set them up. Yeah. So let's leave that for now, but that is a good question and you should definitely read about that. So here we're going to use the only tool we really have is Taylor expansions. So I'm going to restrict to F in C2, maybe 3, I don't remember. So suppose I can take at least two or three partial derivatives. Everything you could possibly think of is dense in whatever function space you want, so who cares? Like if you want to define this operator on a certain function space, feel free. Like just density is your friend. But let's just make it so we can actually do a computation. Fuck. Now I should have notes here. So let's just do this expansion. Expectation of f of bt x. So or let's start it at 0. Minus f of 0. Without less generality, let's just evaluate it at 0, and then you can translate the points. So let's look at tf at 0. So I'll compute expected value of f of b0 minus f of 0 over t. Let's look at this part. So f of x is equal to f of 0 plus df inner product x. No. df apply gradient f dot x plus df at d squared f at x, at 0 xx. Okay, so this is 1/2 here. Okay, so this plus some remainder term which dies off like the length squared. Okay, this is Taylor's theorem for multiple dimensions. I ran out the polynomial to a degree 2. So if I expand this, what does this look like? This is f of
It die
0.
out. Sorry, shouldn't it die out with cubed? So plus O x the length cubed, because we've done the first two, the polynomial of degree 2.
Yeah, you're right. You're right. It should die out like 2. Wait, hold on. If I recall, it dies out. Yeah, you're right, which is dumb because the exposition which I read this in had it dying out at degree 2, but you're right, it should die out at degree 3, which... Okay.
Oh, I mean, I guess maybe we don't need it dies out at degree 3.
We only need it dies out at degree 2, but it's fine.
Wait, but if you only needed it dies out at degree 2, then why do we have the Laplacian term that we consider?
Yeah, you're right. That's a good point. So let's do die out at degree 3.
Okay. Thank you.
It will become clear throughout the this is like a somewhat lengthy computation, but so sum partial f 0 partial I f is 0 xi. Okay, so this is our Taylor expansion that we'll be using, so plus some error. So since I'm subtracting f of 0, we'll just ignore that. And without last generality, you just assume it's 0, so I'm evaluating this. So let's plug in f of bt. Actually, that's all confusing. I'll just keep it. So let's evaluate f of bt and take an expectation. So f of bt is just replace bt. Bt is n-dimensional Brownian motion. One thing that is a theorem is that n-dimensional Brownian motion, if you take the coordinate function, that is now a one-dimensional Brownian motion. That's actually not trivial. Well, it's trivial if you define n-dimensional Brownian motion by just being coordinates of one-dimensionals, but it's not trivial if you define it via these properties. So I'll give references at the end. Okay, so if we plug in bt here, just replace all the x's with bt. And now let's take an expectation. So let me just redo that. Copy here, paste here. Let's replace all the xi's with bt. bti, btj. And then we'll take an expectation. So if we expect on this, well, expected value of f of 0 is just f of 0. And then here, this is a linear sum, so I'll go through all the details. Expected value of this. Well, this is equal to, expectation is linear, so these are coefficients, they pop out. Sum over I, di f of 0, expectation of bt I. Recall here in our properties, plug in right here. I plug in s equals 0 and t equals t. You get that bt is normally distributed 0 around 0, so this is 0. Its expectation is 0. So this term actually just dies out. And then we get 1/2 some coefficients coming from the second partials. And what I'm going to do is I'm going to split up the coefficients. So I'm just going to go split them up like this. So we get partial I, then plus 1/2. So expectation of bti squared plus 1/2 sum of the ones where I is not j, ij, expectation bti, btj. So if you recall, we assumed that the coordinate-wise, in n-dimensional Brownian motion, coordinate-wise, they are independent. Again, that's a result you can prove if you just use axiomatic definition of Brownian motion. of n-dimensional Brownian motion. So this is 0. So the only terms we care about are the diagonal terms. And if you recall, this is a covariance. Well, it's a variance. So all of this can be expressed as this expectation here is now covariance BTI, BTJ. And so that's why I kind of made this matrix picture, because the entire sum, and this is like a standard trick in stochastic processes that like when you're evaluating sums, you do a Taylor expansion. The second term of your Taylor expansion, you use the covariance structure of the process to evaluate it. And so this right here, what is the variance? Well, it's sigma squared. So we got sigma squared over 2 times sum dii. But again, what is dii? What is this sum right here? This is the Laplacian of f. That's 0. And really, nothing special about 0. I could have evaluated everything at y, and then done the same thing here, and I would have gotten the Laplacian of f at a point. So, and the last thing to argue is that the later term vanishes. So O of t cubed. Wait, no. O of x cubed.
Oh wait, if it's little o, then it should be O of t
Yeah,
squared.
it's little o. Yeah, t squared.
Oh, well, yeah, then it's squared.
Yeah, I'm using little. Oh, you're right. I need to like.
Yeah, sorry. That's...
So Greg Lawler was flaming me for this in one of my talks. He's like, James, you're using too many. I just doxed myself. You're using your big O and little o look the same, and you need to not do that. And I felt very embarrassed. So I'll do this little curly for a little while. But yeah, so this part is the reason this dies off is much harder to explain. So I will give an intuitive reason why it dies off, because I'm all about intuition and avoiding having to talk about measure theory. I would love to talk about measure theory, but that's not what this talk is about. So let's look at a fundamental property of Brownian motion, which is, I mean, believable when you look at the drawings, but also just shocking. So I'm not being... There we go. Let me shake more. Okay, so this is what like a typical Brownian motion path looks like, probably. Kind of self-similar, but like it is just jagged edges everywhere. Now, here's a fact. I guess slash exercise if you want. This curve right here, t goes to bt, is almost surely nowhere differentiable. So that's not surprising. What might be surprising is, so let's look at another thing. Let's say I have some type of curve in R2, in R. So say I have some function, and it pass out a curve in here. There exists a notion called the variation of the curve. So we might want to look at what the arc length is here. What is this arc length? And there's a definition for this in terms of the function. So this is like f of t. This is t. And you can find like the arc length of the function from like a to b. This is called the variation of the function, which the total variation of the function from a to b. Now, one thing that might be surprising, and so that would give you this length here. Now, what's an incredibly surprising fact, and you can formally define this, it's the sup over all partitions 0 or a less than t1 less than, so t0 is a up to tn equals b of the sum ti, where the indices are correct, and I won't get them right. But it's this sum right here. And now what's incredibly surprising is another fact. For all a less than b, and so almost surely this property holds. Almost surely, for all a less than b, the Brownian motion curve has infinite variation. Variation from A to B. So under this interpretation of it being arc length, if I look at any small interval, this has infinite length. No matter how small I make it, the length on that curve is infinite. This is why a lot of things are very difficult in stochastic calculus. This is why Ito's lemma is a thing, for example. And why integrating, when people write this, they write integrate with respect to Brownian motion. They don't actually mean integrate, because if you recall, like for a Riemann integral, the way you define it is you look at partitions like this, and you need functions to have finite variation. Like you need at least like this thing to have finite variation. Brownian motion doesn't. This is why. But a fun fact is that if I put a square here, call that QV, it's finite everywhere. So it's weird that like this linear variation is always infinite, and this quadratic variation is always finite. And so the quadratic variation being finite is why if I put a bt here, or bx, this actually goes to 0. And this actually goes to 0 in this limit, well, not bt, not bx, bt. This, like the function here, which is little o of x squared, if I plug in bt, and I take this limit here, this actually dies off. So yeah, that is it. So that's a cool, and that would prove that we get the Laplacian here. I forgot to pick up a factor of t, didn't I? Where did I forget the... No, that died off. There's a factor of t here somewhere. Oh, yeah, the variance being t. Yeah, this variance is t, and so then when I divide by t, now it dies. Now that dies off. There we go. Okay. But ultimately, this computation would give you that the infinitesimal generator, the Brownian motion, is the Laplacian. And another way of viewing this thing right here is this is like the partial derivative of f back to t. Actually, I'm spewing nonsense. Hold on. No, I'm spewing nonsense. So let me, what time is it? Okay, I guess I've gone long enough. So let me end here with saying how you would solve the heat equation. So a couple ways to solve the heat equation. So we have the heat equation. Recall or observe. The heat equation is defined, so we have a, let's do Rn first. So we have, we're looking at a function, which is of u from 0 infinity cross Rn to R, which is giving us a temperature at a time and place, temp. Or it could be a concentration of particles or something like that. But let's just say temperature for now. So what is the problem we're trying to solve? We have an initial temperature distribution, u of 0x equal to some function f of x for all x. Let's assume this is C2. And then we now have we want the change in u over time to be equal to the average rate of change, or the Laplacian, not average, the average change in the mean value of x. So we want this to be true. So Laplacian, recall, is the sum of the second partials, and here are spatial partials only. Okay. So I claim we've already solved this equation with this computation right here. This computation solves this equation. So I claim that the function, which is given by u of tx, to be, take a Brownian motion and start at x. So I'll take Brownian motion, start at x. So let me just draw it out. we have an initial temperature distribution. We have a point x. I claim, so this is at x0, we have some temperature here. Take Brownian motion, run it for t seconds. We get some distribution of values, which it could be. So like remember, it's a random curve, so it's like randomly going somewhere. So bt, which it started at x. I claim just take what the initial temperature was at that point, take the expected value of that. That is a solution to the heat equation. So the expected value of f of btx solves the heat equation in Rn, which is very cool. And if you run through the computation, this proves it actually. So
wait, sorry, what f?
Yeah, u.
Oh, okay. F. Wait. F is u.
No, f is u here.
Oh, u0. Yes.
Yeah,
okay.
u0 is f. So the f is the initial temperature distribution. So u0, so ut is basically, look at all possible ways that a particle starting at x could have diffused over t seconds. So it could be some crazy range of things. And look at the average value of f over that. Average value of the initial temperature distribution. And that should be your temperature right here after time t. So it's like all of these temperatures have diffused towards x. And given like a net. That's kind of the way I interpret this. But we can actually push this further. So people who've seen the heat equation will know that solving the heat equation in a bounded domain is much more difficult. Because really, this equation is easy with the Fourier transform. Like, I did not need to do this. I could have just taken a Fourier transform, done algebra, take the inverse Fourier transform, done. But the moment that you're not over all of Rn, the moment you're over some bounded domain omega, you get a problem. Or not omega, let's do d. Now you get a problem. Because you can't Fourier transform. You got to be able to integrate over all of Rn, and you can't do that if you don't have a function over all of Rn. So, but this method is perfectly fine. So let's see how we would do this, just with a bit of adjustment. So now we have a bounded domain D, we have an initial temperature distribution F, and we have a point X. What should be our solution? Well, motivated by this, we want to take Brownian motion and run it for a certain time, t. So x, let's say run Brownian motion to time t. Now for every sample path, so we're expecting over some Brownian motion starting at x. For every sample path, so for the indicator function of where bt is still inside is still inside d. So for every sample path that stays inside d, aka I never hit the boundary, to that sample path there is no boundary. Hence, let's just do the boundaryless solution for that sample path. For every sample path that did hit the boundary, let's hit the boundary, and let's look at, so the average value of these right here. So f, so let's look at when it does hit the boundary, and let's just take the value there. So plus indicator bt, bt in d, pt not in d, b tau not in d. Okay, let's let tau, consider a new random variable tau, which is going to be the inf over all time t, such that bt, so tau x, I guess, depending on x, btx goes away from the boundary, so is not in d. Smallest time that we leave the region. So let's look at here. Let's look at the indicator function of this. So I guess S here for all S less than t. Indicator function, there exists S less than or equal to t such that BS is not in D. And then you just take F of B tau, so the first time that you hit the boundary. Expect over all of that, that's your new solution to the heat equation. So yeah, that will be the end of my talk. Any questions?
One question right on this section,
Yeah.
which is like, how do you understand the steady state case once, like, say, all your paths have kind of equilibrated out to the whatever the boundary condition makes it?
You're saying like, how do I make sense of a time t goes into infinity?
Yes.
That's a good question, and frankly, I have no idea. I think that the steady state case of the heat equation is a Laplacian equation here. So, in a sense, there should be some type of convergence to the Laplacian equation that we should be able to see. And I don't know how you interpret that stochastically.
Interesting. Okay, yeah, no problem. Thanks.
Yeah, all right, let me stop the broadcast and the recording. Any other questions?